The Big Bang. Around 10 to the negative 43 seconds, the universe begins with a cataclysm that generates space and time, as well as all the matter and energy the universe will ever hold. For an incomprehensibly small fraction of a second, the universe is an infinitely dense, hot fireball. The prevailing theory describes a peculiar form of energy that can suddenly push out the fabric of space. At 10 to the negative 35 seconds to 10 to the negative 33 seconds, a runaway process called inflation causes a vast expansion of space filled with this energy. The inflationary period is stopped only when this energy is transformed into matter and energy as we know it. The universe takes shape around 10 to the negative 6 seconds. After inflation, 1/millionth of a second after the Big Bang, the universe continues to expand, but not nearly so quickly. As it expands, it becomes less dense and cools. The most basic forces in nature become distinct. First is gravity, then the strong force, which holds nuclei of atoms together, followed by the weak and electromagnetic forces. By the first second, the universe is made up of fundamental particles and energy, quarks, electrons, photons, neutrinos, and less familiar types. These particles smash together to form protons and neutrons. Around 3 seconds after the Big Bang, formation of basic elements happen. Protons and neutrons come together to form the nuclei of simple elements, hydrogen, helium, and lithium. It will take another 300,000 years for electrons to be captured into orbits around these nuclei to form stable atoms. The Radiation Era. 10,000 years just after the Big Bang. The first major era in the history of the universe is one in which most of the energy is in the form of radiation of different wavelengths of light, X-rays, radio waves, and ultraviolet rays. This energy is the remnant of the primordial fireball, and as the universe expands, the waves of radiation are stretched and diluted until today, they make up the faint glow of microwaves which bathe the entire universe. The era of matter domination starts 300,000 years after the Big Bang. At this moment, the energy in matter and the energy in radiation are equal. But as the relentless expansion continues, the waves of light are stretched to lower and lower energy, while the matter travels onward largely unaffected. At about this time, neutral atoms are formed as electrons link up with hydrogen and helium nuclei. The microwave background radiation hails from this moment, and thus gives us a direct picture of how matter was distributed at this early time. 300 million years after the Big Bang marks the birth of stars and galaxies. Gravity amplifies slight irregularities in the density of the primordial gas. Even as the universe continues to expand rapidly, pockets of gas become more and more dense. Stars ignite within these pockets, and groups of stars become the earliest galaxies. This point is still perhaps 12 to 15 billion years before the present. 5 billion years before the present marks the birth of the Sun. The Sun forms within a cloud of gas in a spiral arm of the Milky Way galaxy. A vast disk of gas and debris that swirls around this new star gives birth to planets, moons, and asteroids. Earth is the third planet out. Earliest life form in Earth started around 3.8 billion years ago. The Earth has cooled and an atmosphere develops. Microscopic living cells, neither plants nor animals, begin to evolve and flourish in Earth's many volcanic environments. Primitive animals appear around 700 million years ago. These are mostly flatworms, jellyfish, and algae. By 570 million years before the present time, large numbers of creatures with hard shells suddenly appear. The first mammals appear around 200 million years ago. The first mammals evolved from a class of reptiles that evolved mammalian traits, such as a segmented jaw and a series of bones that make up the inner ear. Dinosaurs become extinct around 65 million years ago. An asteroid or comet slams into the northern part of the Yucatan Peninsula in Mexico. This worldwide cataclysm brings to an end the long age of the dinosaurs and allows mammals to diversify and expand their ranges. Homo sapiens evolved around 600,000 years ago. Our earliest ancestors evolved in Africa from a line of creatures that descended from apes. Supernova 1987A explodes way back 170,000 years ago. This is a star that explodes in a dwarf galaxy known as the Large Magellanic Cloud that lies just beyond the Milky Way. The star, known in modern times as Sanjalik 69-202, is a blue supergiant 25 times more massive than the Sun. Such explosions distribute all the common elements such as oxygen, carbon, nitrogen, calcium, and iron into interstellar space where they enrich clouds of hydrogen and helium that are about to form new stars. They also create the heavier elements, such as gold, silver, lead, and uranium, and distribute these as well. Their remnants generate the cosmic rays which lead to mutation and evolution in living cells. These supernovae, then, are key to the evolution of the universe and to life itself. In 1054 AD, the Crab Supernova appears. A new star in the constellation Taurus outshines Venus. Chinese, Japanese, and Native American observers record the appearance of a supernova. It is not, however, recorded in Europe, most likely as a consequence of lack of study of nature during the Dark Ages. The remnants of this explosion are visible today as the Crab Nebula. Within the nebula, astronomers have found a pulsar, the ultradense remains of a star that blew up. In 1609 AD, Galileo builds the first telescope. 5 years after the appearance of the great supernova of 1604, Galileo builds his first telescope. He sees the moons of Jupiter, Saturn's rings, the phases of Venus, and the stars in the Milky Way. He publishes the news the following year in The Starry Messenger. In 1665, Isaac Newton described gravity. At the age of 23, young Isaac Newton realizes that gravitational force accounts for falling bodies on Earth as well as the motion of the Moon and the planets in orbit. This is a revolutionary step in the history of thought, as it extends the influence of earthly behavior to the realm of the heavens. One set of laws, discovered and tested on our planet, will be seen to govern the entire universe. In 1905, Albert Einstein publishes Theory of Relativity. The first of his many seminal contributions to 20th century science, relativity recognizes the speed of light as the absolute speed limit in the universe and, as such, unites the previously separate concepts of space and time into a unified spacetime. 11 years later, his general theory of relativity replaces Newton's model of gravity with one in which the gravitational force is interpreted as the response of bodies to distortions in spacetime which matter itself creates. Predictions of black holes and an expanding universe are immediate consequences of this revolutionary theory, which remains unchallenged today as our description of the cosmos. In 1929, Edwin Hubble discovers that the universe is expanding. The astronomer Edwin Hubble uses the new 100-inch telescope on Mount Wilson in Southern California to discover that the farther away a galaxy is, the more its light is shifted to red. And the redder a galaxy's light, the faster it is moving away from us. By describing this Doppler shift, Hubble proves that the universe is not static, but is expanding in all directions. He also discovers that galaxies are much further away than anyone had thought. In 1960 marks the discovery of quasars. Alan Sandage and Thomas Matthews find sources of intense radio energy, calling them quasi-stellar radio sources. 4 years later, Martin Schmidt would discover that these sources lie at the edge of the visible universe. In recent years, astronomers have realized that they are gigantic black holes at the centers of young galaxies into which matter is heated to high temperatures and glows brightly as it rushes in. In 1964 marks the discovery of microwave background radiation. Scientists at the Bell Telephone Laboratories discovered microwave radiation that bathes the Earth from all directions in space. This radiation is the afterglow of the Big Bang. In 1967, pulsars were discovered. A graduate student, Jocelyn Bell, and her professor, Anthony Hewish, discover intense pulsating sources of radio energy known as pulsars. Pulsars were the first known examples of neutron stars, extremely dense objects that form in the wake of some supernovae. The Crab Pulsar is the remnant of the bright supernova recorded by Native Americans and cultures around the world in the year 1054 AD. In 1987, light from supernova 1987A reaches Earth. The light from this supernova reaches Earth 170,000 years after its parent star exploded. Underground sensors in the United States and Japan first detect a wave of subatomic particles, known as neutrinos, from the explosion. Astronomers rushed to telescopes in the southern hemisphere to study the progress of the explosion and perfect models describing the violent deaths of large stars. In 1990, Hubble Space Telescope was launched. The 12-ton telescope, equipped with a 94-inch mirror, is sent into orbit by astronauts aboard the Space Shuttle Discovery. Within 2 months, a flaw in its mirror is discovered, placing in jeopardy the largest investment ever in astronomy. In 1990, the Big Bang theory is confirmed. Astronomers used the new Cosmic Background Explorer satellite, COBE, to take a detailed spectrum of the microwave background radiation. These studies showed that the radiation is in nearly perfect agreement with the Big Bang theory. 2 years later, scientists used the same instrument to discover minute variations in the background radiation, the earliest known evidence of structure in the universe. In 1993, the Hubble Space Telescope was repaired. Astronauts aboard the Space Shuttle Endeavour succeed in correcting Hubble's flawed optics, ushering in a spectacular new age of astronomy from space. Hubble's greatest legacy so far are the detailed images of galaxies near the limits of the visible universe. After 100 trillion years in the future, the stellar era will end. Astronomers assume that the universe will gradually wither away, provided it keeps on expanding and does not recollapse under the pull of its own gravity. During the stelliferous era, from 10,000 years to 100 trillion years after the Big Bang, most of the energy generated by the universe is in the form of stars burning hydrogen and other elements in their cores. The Degenerate Era is said to be 100 trillion to 1,037 years in the future. This era extends to 10 trillion years after the Big Bang. Most of the mass that we can currently see in the universe is locked up in degenerate stars, those that have blown up and collapsed into black holes and neutron stars, or have withered into white dwarfs. Energy in this era is generated through proton decay and particle annihilation. The black hole era is said to be 1,038 to 10,100 years in the future. This era extends to 10,000 trillion years after the Big Bang. After the epoch of proton decay, the only stellar-like objects remaining are black holes of widely disparate masses, which are actively evaporating during this era, the dark era, times later than 10,100 years in the future. At this late time, protons have decayed and black holes have evaporated. Only the waste products from these processes remain, mostly photons of colossal wavelength, neutrinos, electrons, and positrons. For all intents and purposes, the universe as we know it has dissipated.